So we're getting ready to look at directional derivatives and gradients. So as part of that discussion, we want to start by first thinking about what a partial derivative represents. So if I was given a function f of x and y, what does the partial of f with respect to x represent? Now we've discussed that that is the slope of the graph in the direction of the x-coordinate, or the slope of the graph parallel to the x-axis. We can similarly have an interpretation for the partial of f with respect to y, and that would represent the slope of the graph with respect to y, or the slope in the direction parallel to the y-axis. But now we're looking at a function of two variables. So at any given point, there are an infinite number of directions by which we can approach that point xy. So we may be interested in rates of change in directions other than those that are parallel to the x-axis or those that are parallel to the y-axis. So the idea is, how do we find rates of change in directions other than those that are parallel to the coordinate axes? And the answer to that is we use something known as the directional derivative. Now, the directional derivative we'll talk about a little more in a little bit, but for now we're focusing on the partial derivatives and how they can be relevant to what we're doing. So the first thing I want to show you is the gradient. Now, the gradient is an important vector associated with a differentiable function. So let f of x and y be a differentiable function. So this is going to be important. It has to be differentiable, which means that the derivative exists and is continuous. The gradient of the function is a vector. So this is important, is a vector. So when I talk about the gradient, it's going to be a vector. And this vector contains the partial derivatives of that function. So notice I have this upside down triangle. It's delta. So we have del f, or the gradient of f, is a vector. And since my function only was a function of x and y, there's only two partial derivatives, so the gradient vector only has two components. So the x component of the partial derivative is the partial derivative with respect to x, and the y component is the partial derivative with respect to y. So for example, if I had a function f of x and y equal to something like 2x minus 4y, then I can find the gradient of that function. The gradient of f of x and y would be a vector. In the x component, I take the partial derivative with respect to x. In this case, that would be 2. The y component would be the partial derivative with respect to y. In this case, that would be negative 4. And this would be my gradient vector. Okay? So keep in mind as we talk about the gradient that it is in fact a vector. And this vector contains the partial derivative of the function with respect to x and the partial derivative of the function with respect to y. So why is the gradient important to us? Well, it has some properties that are extremely useful. So what we want to do is just point out a couple of those properties. So first of all, the gradient vector, reminder it is a vector, it points in the direction of greatest increase. It points at the direction that the function is increasing most quickly. The second important piece of information that the gradient or property it has is that it's normal to level curves. and by extension to level surfaces. So remember, normal is that idea of being orthogonal or perpendicular. Those are going to be important properties as we move forward in the class. So these two properties are really important, and we will be talking about other properties as we continue our discussion of directional derivatives.